All right, we are back. Sorry about that. I got things loaded and we are good. All right. Okay, we are on number 9. And let's get started. I'm going to drag this over here so I can read it as I go. So we have our formula is power factor is equal to true power over power apparent. And so that gives us true power over apparent power. And we are trying to get to, we are at a 63, so that's going to be 0.63 is equal to 25,000 watts over P true. So we don't have P true yet, but we can get it. So we have really a triangle worked out. With 25,000 on this side. We don't know this side. We know the cosine of theta is 0.63. Suffice to say, we can find this other side by swapping these two sides. Using algebra, basically all we do is swap those two sides, though. So, true power, or this isn't true power. I apologize, that's apparent power. All right. Apparent power is equal to 25 kilowatts over 0.63. So let's do that. There's my... I think I'm going to go from this screen all the time now. That being said, I'm going to drag this over here. Okay. We're really trying to figure out this side overall. That's our goal, is to find out that side. Yeah. Okay. So we're trying to figure out, let's see, apparent power. Calculator. That's where we were. So we've got 25,000. That's 250,000. Back up one. 25,000 divided by 0.63 gives us 39,682. That's volt amps. And to get to 95%, we'll just swap this. It's going to be 25 kilowatts over 0.95. 25 kilowatts divided by 0.95. Okay, 26,315.78. I'm going to give this the 0.5 that it deserves also. So, we're trying to go from this triangle to this triangle. Still having 25,000 here because that's not going to change, but we want to get the top to 26,315.8. So, what changes is this side. So we need to find those two sides and find the difference between them. That's very simply Pythagorean theorem. So we're going to take the uh, 25,000 squared plus 3968. Oh, wait. Let's do our formula. Since we're trying to find one of the sides that's not the hypotenuse, Pythagorean theorem is going to change slightly. It's actually going to be b is equal to the square root of c squared minus a squared, which is taking a squared plus b squared equals c squared, subtracting a squared from both sides, and then taking the square root of both sides. The square root cancels that, and we're done. That's how we got that formula. So let's do it in our calculators. We have 39,682.5 squared minus 2,500,000 squared. So we got that. Then we're going to take the square root wherever that is. Oh, there it is. Take the square root of that, and that gives us 30,817.2. All right, now we do the other one. 26,315.8 squared plus 25,000 squared. It's supposed to be minus. Hang on. Clear. 26,315.8 squared minus 25,000 squared. And then we take the square root of that. 8,217 point, we'll round that just to 8,217. And this is vars. So, now that we've found that, all we have to do is click the right button, and that is subtract 3817 minus 8 to 17. The 17 stayed the same. We get 22,600. So let's go back to Socrative. The only one that's close is C. There it is. 22.75 capacitive kilovars. Let's compare what we did to their... Okay, they used tangent. They found the degree that is... They found the degree that is 65%, and they found the degree that is 95%. They subtracted those two degrees from each other, and they figured out how much of an angle is different between the two. And they figured out how much this side would have to change for this angle to be that. They definitely did it the quickest. If you were an expert with trigonometry, this would have been definitely the easiest way to do it. I think what I showed is an easier way for you guys to do it with the formulas you've already been given, which is find what the sides are, find your vars, and subtract the vars that you have from the vars that you want to be. Okay. Let's move right along into the next one. On to the next one. An industrial plant has a total load of 1,513 voltamps, kilovoltamps, has a power factor of 80%, which results in 908 kilovars of reactive power. You know, it occurs to me, I could have just left everything in kilo in that last question and not put all the zeros at the end of things. Good thing to think about. Which results in 908 kilovars of reactive power. How many 45 kilovar units would be required to correct the out-of-phase condition without causing a leading power factor? This one's super easy. We have 908 kilovars of reactive power, and we're using 45 kilovar capacitors, or units. So we're going to take 908 and divide it by 45, and the whole number is 20. So of our options, 10 and 15 wouldn't get us a correct the out of phase condition. 25 would take us beyond where we wanted to be. So 20 is our answer. It's as simple as dividing. All right, 11. Where motors that are jogged, plugged, or reversed have power factor correction, where must motors that are jogged, plugged, or reversed have power factor correction capacitors installed? That will be on the line side of the starter. Let's see. And this will help it correct the power factor for things that don't just come on, go off. Come on, go off. It will be... Oh, my pen's too close. It will correct it good enough, and it won't have to do all the build up whenever the capacitors kick on or off. Don't have an explanation added. Circuits that contain both resistance and reactance must have a power factor between. So power factor is a percentage, so it has to be between 0 and 100%. And then angles are based on triangles, and they have to be between 0 and 90. That's all that there is to it. There it is. So, shame. People don't know. Why would it be 100 degrees and not 90 degrees? Why would it not be 100%? All right. Well, that is it for this one. Let me find my button to turn off the stream. I will see you guys in the next one.